Hello everyone. Today we are going to read chapter 8 Force and Pressure. This is a long chapter, so we are going to read it in two parts. Today we are going to read the part 1. In class 7, you have learnt how objects move. Do you recall how we can decide whether an object is moving faster than the other? What does the distance moved by an object in unit time indicate? You also know that a moving object like a ball rolling on a ground slows down. Sometimes it may change its direction of motion. It is also possible that the ball may slow down and also change its direction. Have you ever wondered what makes an object slow down or go faster or change its direction of motion? Let us recall some of our everyday experiences. What do you do to make a football move? What do you do to make a moving ball move faster? How does a goalkeeper stop a ball? How a hockey player changes the direction of the moving ball with the flick of the stick. How do fielders stop a ball hit by a batsman? In all these situations, the ball is either made to move faster or slower, or its direction of motion is changed. We often say that a force has been applied on a ball when it is kicked, pushed, thrown, or flicked. What is a force? What can it do to bodies on which it is applied? We shall seek answers to such questions in this chapter. Force, a push or a pull. Actions like picking, opening, shutting, kicking, hitting, lifting, flicking, pushing, pulling are often used to describe certain tasks. Each of these actions usually result in some kind of change in the state of motion of an object. Can these terms be replaced with one or more terms? Let us find out. Activity 8.1. Table 8.1 gives some examples of familiar situations involving motion of objects. You can add more such situations or replace those given here. Try to identify action involved in each case as a push and or a pull and record your observations. One example has been given to help you. Description of the situation. Moving a book placed on a table, opening or shutting a door, drawing a bucket of water from a well, a football player taking a penalty kick, a cricket ball hit by a batsman, moving a loaded cart, opening a drawer. Do you notice that each of the actions can be grouped as a pull or a push or both? Can we infer from this that to move an object, it has to be pushed or pulled? In science, a push or a pull on an object is called a force. Thus, we can say that the motion imparted to objects was due to the action of a force. When does a force come into play? Let us find out. I learnt in class 6 that a magnet attracts a piece of iron towards it. Is attraction also a pull? What about repulsion between similar poles of two magnets? Is it a pull or a push? Forces are due to an interaction. Suppose a man is standing behind a stationary car. Will the car move due to his presence? Suppose the man now begins to push the car. That is, he applies a force on it. The car may begin to move in the direction of the applied force. Note that the man has to push the car to make it move. Figure 8.3 shows three situations that may be familiar to you. Can you decide who is pulling and who is pushing in these cases? In figure 8.3a, both the girls appear to push each other while the pair of girls in figure 8.3b are trying to pull each other. Similarly, the cow and the man in figure 8.3c appear to pull each other. The girls in the two situations shown here are applying force on each other. Is it also true for the man and the cow? From these examples, we can infer that at least two objects must interact for a force to come into play. Thus, an interaction of an object with another object results in a force between the two objects. Exploring forces. Let us try to learn more about forces. Activity 8.2. Choose a heavy object like a table or a box, which you can move only by pushing hard. Try to push it all by yourself. Can you move it? Now ask one of your friends to help you in pushing it in the same direction. Is it easier to move it now? Can you explain why? Now push the same object but ask your friend to push it from the opposite side. Does the object move? If it does, note the direction in which it moves. Can you guess which one of you is applying a larger force? Have you ever seen a game of tug of war? In this game, two teams pull at a rope in opposite directions. Members of both the teams try to pull the rope in their direction. Sometimes the rope simply does not move. Is it not similar to the situation shown in figure 8.3b? The team that pulls harder, that is applies a larger force, finally wins the game. What do these examples suggest about the nature of force? Forces applied on an object in the same direction add to one another. Now recall what happened when you and your friend pushed the heavy box in the same direction in activity 8.2. If the two forces act in the opposite directions on an object, the net force acting on it is the difference between the two forces. What did you observe in activity 8.2 when both of you were pushing the heavy box from opposite directions? Recall that in the tug of war, when two teams pull equally hard, the rope does not move in any direction. So we learn that a force could be larger or smaller than the other or equal to each other. The strength of a force is usually expressed by its magnitude. We have also to specify the direction in which a force acts. Also, if the direction or the magnitude of the applied force changes, its effect also changes. Does it mean that the net force on an object is zero if the two forces acting on it in opposite direction are equal? In general, more than one force may be acting on an object. However, the effect on the object is due to the net force acting on it. A force can change the state of motion. Let us now find out what happens when a force acts on an object. Activity 8.3. Take a rubber ball and place it on a level surface such as the tabletop or a concrete floor. Now gently push the ball along the level surface. Does the ball begin to move? Push the ball again while it is still moving. Is there any change in its speed? Does it increase or decrease? Next, place your palm in front of the moving ball. Remove your palm as soon as the moving ball touches it. Does your palm apply a force on the ball? What happens to the speed of the ball now? Does it increase or decrease? What would happen if you let your palm hold the moving ball? You might recall similar situations. For example, while taking a penalty kick in football, the player applies a force on the ball. Before being hit, the ball was at rest and so its speed was zero. The applied force makes the ball move towards the goal. Suppose the goalkeeper dives or jumps up to save the goal. By this action, the goalkeeper tries to apply a force on the moving ball. The force applied by him can stop or deflect the ball, saving a goal being scored. If the goalkeeper succeeds in stopping the ball, its speed decreases to 0. These observations suggest that a force applied on an object may change its speed. If the force applied on the object is in the direction of its motion, the speed of the object increases. If the force is applied in the direction opposite to the direction of motion, then it results in a decrease in the speed of the object. I have seen children competing with one another in moving a rubber tire or a ring by pushing it. I now understand why the speed of the tire increases whenever it is pushed. Paheli is curious to know whether application of a force can only change the speed of an object. Let us find out. Activity 8.4. Take a ball and place it on a level surface as you did in activity 11.3. Make the ball move by giving it a push. Now place a ruler in its path as shown in figure 8.8b. In doing so, you would apply a force on the moving ball. Does the ball continue to move in the same direction after it strikes the ruler? Repeat the activity and try to obstruct the moving ball by placing the ruler in such a way that it makes different angles to its path. In each case, note your observations about the direction of motion of the ball after it strikes the ruler. Let us consider some more examples. In a game of volleyball, players often push the moving ball to their teammates to make a winning move. Sometimes the ball is returned to the other side of the court by pushing or smashing it. In cricket, a batsman plays his or her shot by applying a force on the ball with the bat. Is there any change in the direction of motion of the ball in these cases? In all these examples, the speed and the direction of the moving ball change due to the application of a force. Can you give a few more examples of this kind? A change in either the speed of an object or its direction of motion or both is described as a change in its state of motion. Thus, a force may bring a change in the state of motion of an object. State of motion. The state of motion of an object is described by its speed and the direction of motion. The state of rest is considered to be the state of zero speed. An object may be at rest or in motion, both are its states of motion. Does it mean that the application of a force would always result in a change in the state of motion of the object? Let us find out. It is common experience that many a time application of force does not result in a change in the state of motion. For example, a heavy box may not move at all even if you apply the maximum force that you can exert. Again, no effect of force is observed when you try to push a wall. Force can change the shape of an object. Some situations have been given in column 1 of table 8.2 in which objects are not free to move. Column 2 of the table suggests the manner in which a force can be applied on each object, while column 3 shows a diagram of the action. Try to observe the effect of force in as many situations as possible. You can also add similar situations using available material from your environment. Note your observations in column 4 and 5 of the table. Description of situation and how to apply force. A lump of dough in a plate. Apply force by pressing it down with your hands. Spring fixed to the seat of a bicycle. Apply force by sitting on the seat. A rubber band suspended from a hook nail fixed on a wall. Apply force by hanging a weight or by pulling its free end. A plastic or metal scale placed between two bricks. Apply force by putting a weight at the center of the scale. What do you conclude from the observations noted in table 8.2? What happens when you apply a force on an inflated balloon by pressing it between your palms? What happens to the shape of a ball of dough when it is rolled to make a chapati? What happens when you press a rubber ball placed on the table? In all these examples, you saw that the application of force on an object may change its shape. Having performed all the above activities, you would have realized that a force may make an object move from rest, may change the speed of an object if it is moving, may change the direction of motion of an object, may bring about a change in the shape of an object, may cause some or all of these effects. While a force may cause one or more of these effects, it is important to remember that none of these actions can take place without the action of a force. Thus, an object cannot move by itself, it cannot change speed by itself, it cannot change direction by itself, and its shape cannot change by itself. Contact forces. Muscular force. Can you push or lift a book lying on a table without touching it? Can you lift a bucket of water without holding it? Generally, to apply a force on an object, your body has to be in contact with the object. The contact may also be with the help of a stick or a piece of rope. When we push an object like a school bag or lift a bucket of water, where does the force come from? This force is caused by the action of muscles in our body. The force resulting due to the action of muscles is known as the muscular force. It is the muscular force that enables us to perform all activities involving movement or bending of our body. In class 7, you have learned that in the process of digestion, the food gets pushed through the alimentary canal. Could it be a muscular force that does it? You also know that lungs expand and contract while we inhale and exhale air during breathing. Where are these muscles located which make breathing possible? Can you list a few more examples of the force exerted by the muscles in your body? Animals also make use of muscular force to carry out their physical activities and other tasks. Animals like bullocks, horses, donkeys, and camels are used to perform various tasks for us. In performing these tasks, they use muscular force. Since muscular force can be applied only when it is in contact with an object, it is also called a contact force. Are there other types of contact forces? Let us find out. Friction. Recall some of your experiences. A ball rolling along the ground gradually slows down and finally comes to rest. When we stop pedaling the bicycle, it gradually slows down and finally comes to a stop. A car or a scooter also comes to rest when its engine is switched off. Similarly, a boat comes to rest if we stop rowing it. Can you add some more such experiences? In all these situations, no force appears to be acting on the objects. Yet their speed gradually decreases and they come to rest after some time. What causes a change in their state of motion? Could some force be acting on them? Can you guess the direction in which the force must be acting in each case? The force responsible for changing the state of motion of objects in all these examples is the force of friction. It is the force of friction between the surface of the ball and the ground that brings the moving ball to rest. Similarly, friction between water and the board brings it to a stop once you stop rowing. The force of friction always acts on all the moving objects, and its direction is always opposite to the direction of motion. Since the force of friction arises due to contact between surfaces, it is also an example of a contact force. You will learn more about this force in chapter 9. You may be wondering whether it is essential for the agent applying a force on an object to be always in contact with it. Let us find out. Non-contact forces. Magnetic force. Take a pair of bar magnets. Place the longer side of one of the magnets over 3 round shaped pencils or wooden rollers as shown in figure 8.10. Now bring one end of the other magnet near the end of the magnet placed on the rollers. Make sure that the two magnets do not touch each other. Observe what happens. Next, bring the other end of the magnet near the same end of the magnet placed on the rollers. Note what happens to the magnet placed on the rollers every time another magnet is brought near it. Does the magnet on the rollers begin to move when the other magnet is brought near it? Does it always move in the direction of the approaching magnet? What do these observations suggest? Does it mean that some force must be acting between the two magnets? You have learnt in class 6 that like poles of two magnets repel each other and unlike poles attract each other. Attraction or repulsion between objects can also be seen as another form of pull or push. Do you have to bring the magnets in contact for observing the force between them? A magnet can exert a force on another magnet without being in contact with it. The force exerted by a magnet is an example of non-contact force. Similarly, the force exerted by a magnet on a piece of iron is also a non-contact force. Electrostatic force. Take a plastic straw and cut it into nearly 2 equal pieces. Suspend one of the pieces from the edge of a table with the help of a piece of thread. Now hold the other piece of straw in your hand and rub its free end with a sheet of paper. Bring the rubbed end of the straw near the suspended straw. Make sure that the two pieces do not touch each other. What do you observe? Next, rub the free end of the suspended piece of straw with a sheet of paper. Again, bring the piece of straw that was rubbed earlier with paper near the free end of the suspended straw. What do you observe now? A straw is said to have acquired electrostatic charge after it has been rubbed with a sheet of paper. Such a straw is an example of a charged body. The force exerted by a charged body on another charged or uncharged body is known as electrostatic force. This force comes into play even when the bodies are not in contact. The electrostatic force, therefore, is another example of a non-contact force. You will learn more about electric charges in chapter 12. Gravitational force. You know that a coin or a pen falls to the ground when it slips off your hand. Leaves and fruits also fall to the ground when they get detached from the plant. Have you ever wondered why is it so? When the coin is held in your hand, it is at rest. As soon as it is released, it begins to move downwards. It is clear that the state of motion of the coin undergoes a change. Can this happen without a force acting on it? Which is this force? Objects or things fall towards the earth because it pulls them. This force is called the force of gravity or just gravity. This is an attractive force. The force of gravity acts on all objects. The force of gravity acts on all of us all the time without or being aware of it. Water begins to flow towards the ground as soon as we open a tap. Water in rivers flows downwards due to the force of gravity. Gravity is not a property of the earth alone. In fact, every object in the universe, whether small or large, exerts a force on every other object. This force is known as the gravitational force. So this was the reading of part 1 of our chapter 8, Force and Pressure. If you have any doubt or query, you can ask me in the comment section below. Also, you can find the links of the playlist and the other chapters in the description box below. Thank you everyone.